In a problem like this, we can use the same kind of rationale to figure out how fast the system is going after the kid jumps onto the merry-go-round. What we say is that the kid has what's known as a point mass angular momentum. It's going to seem a little bit weird because the kid clearly has linear momentum. They're running in a straight line. And we don't think of them as spinning. In fact, I would assume that right now, we're saying that the kid running in a straight line and we're talking about angular momentum, you would probably say, well, the kid isn't going in a circle. The kid isn't spinning around. They're going in a straight line. Well, the way we can do this is a little weird. I want you to imagine that you're on the merry-go-round and you're looking at the kid. If you're on the merry-go-round and looking at the kid, you would have to turn your head to follow the kid. Let's say they don't actually jump onto the merry-go-round, they just keep going. You understand that you would have to turn and swivel to follow the kid? Now, if the kid's running in this direction, your direction of swivel would be this direction, right? Starting from here, your direction of swivel would be like that. Does that make sense? So what we do is we define angular momentum like that. We say the kid has angular momentum relative to the merry-go-round. Now, I'm using a lowercase l, but I don't just draw a line because then it would just look like a 1. That's why it's like a little script L, like it's cursive. That's because we use a lowercase l when talking about a point mass having angular momentum. And we use an uppercase L for an object that's spinning. So this kid's not spinning, this kid's running in a straight line, but we say relative to the merry-go-round, he has angular momentum. And that angular momentum equals R times P times the sine of an angle between them. R is this. R is the line that connects the axis of rotation with the kid. That's what R is. Phi is the angle between the momentum and R. And P is the momentum, MV. Now, I know this seems kind of weird. And to be honest with you, it is kind of weird. But I want you to understand that this isn't fake. They didn't just create this. This works. This is how we can perceive the rotation of the kid, even though they're not rotating. Because when they jump onto the merry-go-round, they are going to add something to the merry-go-round. Now, the kid's not really traveling in a circle. And clearly, where they jump on the merry-go-round will make a difference. If they ran this way and jumped on the merry-go-round, would you expect the merry-go-round to spin at all? No, but that works here, because if they ran that way, the angle would be 0, which means they have no angular momentum if they run right at the pivot point. They only have angular momentum because they are expressly running towards the edge of the merry-go-round. And that gives them angular momentum, and again, I keep using this phrase, relative to the merry-go-round. If they don't jump on the merry-go-round, they don't have angular momentum. They're running in a straight line. It only makes sense to think about their angular momentum when you think about what they're going to do when they get to the merry-go-round. Okay? This would be no different than two ice skaters that are coming towards each other. When they grab their hands, they spin afterwards. You don't perceive them as having angular momentum before they lock hands, but they do. Relative to the point where they're going to rotate, they have angular momentum, and they bring that angular momentum into the problem. Now, this next thing I want to talk to you about is going to be somewhat confusing. But if you're paying any real attention, and you're not treating this like every other Monday and looking down at the floor and such, then are you not a little concerned that as a kid gets closer, R is changing? You guys, doesn't that, if it were me, I'd be a little concerned that, well, it looks like I have a problem because R is never the same amount as they get closer. R seems to be getting smaller. But at the same time, isn't the angle looking like it's getting bigger? You see that? Now, it's hard for me to convince you that this works, but R is getting smaller in the same proportion as sine of the angle is getting bigger. I can prove it to you But to prove it to you, you're going to have to kind of go on a little journey, okay? So I want to prove it to you because it's also going to give us a shortcut, something where we'll probably never use this actually, okay? So follow along. I want to take my picture here and I just want to turn it. Because if I turn it, I can draw something on here that will help. Consider this. I'm drawing a right triangle here, and this right triangle is lined up with the kid's journey, isn't it? It's also lined up with R. This has to be R1. Agreed? That's also the hypotenuse of that triangle. Do you see that? So this side is the opposite side of that triangle, and this has to equal phi. All okay? Well, if you'll recall, sine of phi is opposite over hypotenuse. So the opposite side has got to be R1 sine phi 1. That okay? So now we're talking about this side. So that occurs when the kid is here, but the kid is moving, so eventually the kid will be here, right? Now, I'm hoping you're seeing this, but this has to be R2, and this has to be phi 2. Do you notice that R2 times sine of phi 2 is still going to be the same sized opposite side? So now do you believe me that they change in the same proportion? Go ahead.
Can you make it try like somewhere else? Like it has to be right there.
No, that's just where the two guys were, the 2 points for the person was. But any triangle, I mean, I'm making the triangle here because it's using has to be based on the axis of rotation, and it has to be lined up with the direction the kid's running. So those are the points that I'm using to line it up. Does that make sense? So that's why I drew the triangles the way I did. That okay? So what I'm trying to convince you of is that as long as they are running at a constant speed, this will be the same value no matter what R is. Right? So as they get closer and closer to that point, R sine phi is staying the same value. You guys good so far? Following that? In fact, if you're really paying attention, and if you're not really paying attention, now would be an excellent time to do so. This point here, where the kid jumps on, is when R is smallest. In fact, it's when R is going to be perpendicular to their velocity. Oftentimes, we write this as R perpendicular. I don't know what happened. I apparently drew a line. Doesn't look like it though. Let's try again. R perpendicular times P, where this is the R of closest approach. Meaning when they are closest to the pivot point. So like if they jumped on there and missed the merry-go-round, R would get bigger, and they just keep going in the same direction. But this represents the point where they're closest to the pivot point. You guys follow so far? Is that okay? Let's see how this works in practice, all right? To put this into practice, let's get all these triangles out of here. We don't need them. There. Let's erase all this stuff. We don't need all this stuff. It's all just getting in the way. So I'm just going to get all this out of the way so we can start a problem. So let's say that the kid is running towards the merry-go-round. And let's say that the merry-go-round is the same size as it was on Friday. and that it's a 150 kilogram merry-go-round and has a 2-meter radius. And let's say that the kid is running at 2 meters per second and is the same 30 kilogram kid as before. And they're gonna run and jump onto the edge of the merry-go-round. The question, how fast is the merry-go-round going after they jump onto the merry-go-round? Everybody following along with my question? Okay. This is a conservation of angular momentum question. It's a collision between the kid and the merry-go-round. In fact, it has the same name as the collisions we talked about before. This is a perfectly inelastic collision because the kid joins the merry-go-round and stays on it. So the kid makes to the edge of the merry-go-round, jumps on, and now the kid and merry-go-round are spinning. Does that make sense? Now, I do need to say this to you. Linear momentum isn't conserved here in this collision because after the kid jumps onto the merry-go-round doesn't suddenly start moving this way, right? In the linear momentum problems, whatever the linear momentum of the system was, that has to be conserved. That doesn't happen here because although the kid is pushing on the merry-go-round, right? When the kid gets here, the kid pushes on the merry-go-round this way. There's a force from the ground on the merry-go-round this way, right? The merry-go-round is fixed to the ground, isn't it? So that force keeps the merry-go-round from going anywhere. In fact, the net force on the merry-go-round is 0. And that's why the merry-go-round stays in place. But the net torque isn't 0. Because this force is at the center, it causes no torque. But this force isn't at the center, it causes a torque, and that's why the merry-go-round spins. One thing to think about, though, is if I set this problem up in some kind of impossible land, like I put a big merry-go-round shaped disc on an icy lake, and you were running towards this disc, and you jumped on the disc, and the disc was on ice, and there was no thing holding it in place, then the disc would go this way because there'd be no force on it holding it in place. But the kid landing on the side of it would still cause the disc to spin. Under that situation, it would be 2 things happening in that collision. Conservation of linear momentum, that would explain how fast the disc moves after the kid jumps on it, and conservation of angular momentum, which would explain how fast the disc spins after the kid jumps on it. So if there's nothing holding it in place, you get both things. We're going to say there's something holding it in place, so that we only have to worry about one thing at a time. Okay? So let's do the problem. The kid has angular momentum. This is before he jumps on there. And then afterwards, the system will have angular momentum. I'm using the capital L here because when the kid jumps on the merry-go-round, the whole merry-go-round spins. So that's why I'm using the capital L there. But I'm using the lowercase l for the kid because he's just running in a straight line. All good so far? Now, I don't know where the kid begins. I don't know what the original R is, and I don't know what this angle is, and I don't care. In this problem, I can surmise that the kid slowly advanced until he was right here, jumped up, and at that instant, right as he's about to land, remember, a collision is the instantaneous moment before contact and the instantaneous moment after. So instantaneously before contact, that's R, because he's jumping right on the edge. And in this case, they are traveling perpendicular to R at that instant. So my angular momentum before the collision will be R perpendicular times P, and P is just mv. However, afterwards, we got a whole bunch of things to think about. First, moment of inertia of the disc, for sure. Right, the merry-go-round. Plus, moment of inertia of the kid, because the kid is now part of the disc. Does that make sense? All times omega. This is how we figure out how fast the system's going after the collision. Now, I don't think this part's very hard. Let's see if we can work it out. R perpendicular is just the radius of the disk, right? So that's 2 meters, because that's the merry-go-round. M is the mass of the kid. That's 30 kilograms. And how fast is the kid running? 2 meters per second. Yep. All right. Let's see if we can do the merry-go-round part. We did some of this last week, right? So you should have it in your notes. Like, you should know what the moment of inertia of this merry-go-round is. I'm using the same merry-go-round from last week. But if you don't remember, what kind of shape is it? A disc? What's the moment of inertia of a disc? 1/2 m r squared. All right, we can do that. Now we have to add to that the moment of inertia of the kid. He's a point mass. How do we calculate the moment of inertia of a point mass? Go ahead. mx squared. Kid's 30 kilograms, and he is 2 meters from the center. All good? Now, this is just math parts. Putting in the numbers is the least interesting thing here. We're doing this because, kind of give you a brain a break and have an example question. But there is something I want you to see here, so I want to carry this out to the end. 2 times 30 times 2 is going to be 120. And that's going to be kilograms meters squared per second, right? I got a meters here and a meters here, so meters squared. 1/2 times 150 times 2 squared is just 150 times 2, or 300. And that unit is kilograms meters squared. Right, 150 kilograms times 2 meters squared. Plus 30 times 2 squared is 120 kilogram meters squared times omega. Now, that's going to be 120 kilograms meters squared per second divided by 420 kilogram meters squared equals omega. I know I don't normally write out the units like this, but this is what I want you to see. So are we all up to date with me here? We're all caught up? Kilograms meter squared cancels kilogram meter squared. Now I can just do the division here, and we get, 120 divided by 420, and that's 0.286. But my units are nothings per second, right? Because all the top units canceled out. What do you think the nothings are here? Good job. Good job. I'm 1 for 3 getting the answer from students in AP Physics 1 for that question, which means you're the only class who said it. In mechanics, it was only 50% as well. So good job, AP Physics 1. Good job, 7th period. Fantastic. Yeah, if the units cancel out and there's no units there, it's radians, not revolutions, not rotations, radians. You should take a minute right now and figure out if energy was gained or energy was lost. I think it's an important question. Since last time I gave you an example where energy is gained, you should see what happens here. I don't think you need me to do that, so I'm going to take a breather. But I will give you a hint that probably 1/2 mv squared is what you'll use for the kid before, because he's just running in a straight line. And 1/2 I omega squared is what you'll use after. Does that make sense? Because you have all the stuff. You have I and you have omega. You can do it. I believe. 60 joules here. Is that what you guys got? 17 joules here. Is that what you guys got? I'm holding on. You got 4.9? Yeah. One of us made a mistake. Well, let's see. I did 1/2 times 420 times 0.286 squared. Let's see. 0.286 squared is 0.081796 times 420, which gives me 34.35 times 0.5, which gives me 17. Yeah, I'm pretty happy with 17. Okay. So clearly energy was lost. Well, this is a perfectly inelastic collision, right? Energy is going to be lost. The kids walking to the center isn't a collision. Momentum's conserved, but it wasn't a collision, right? This is a collision. One object hit another object, and they join together. Now, this kid could walk to the center. If they do, I bet the thing speeds up. But that's them adding energy to the system. They're doing work on it when they do that. But the collision's going to lose energy. All right. I got 10 minutes for this one. It's going to be harder. All right? And I'm going to do one that's different than what I did in second and third period because I think this will be a better example. Imagine I have a ball resting on the ground, right here. Okay? And I have let's just use a rod. All right, so imagine we just have a rod like this, and it's being held over here, and somebody's going to let go, and it's going to swing down and hit the ball. Okay? Now, I'm preparing you for, like, the real thing here. Like, this is how baseballs get hit and how they acquire momentum. There's rotational momentum, or angular momentum of the bat, but linear momentum of the ball. Right? Same with hockey, same with golf. You know, in all cases, the stick is being swung in a circular path, so it has some kind of angular momentum, and that gets translated to the ball in the form of linear momentum. Now, the first thing I want to ask you, I don't know if you can do this, but you should be able to. If I just released the meter stick, let's say this is a meter stick, and I just release it. I don't have one sitting right here, of course. But if I just released it, and it's just a rod, and it swings downwards, could you figure out how fast it would be going at the bottom? Just let it go? Is that a problem you can do? Probably. Oh, sorry, desk. Let's see. It's not a particularly hard question. It's a conservation of momentum question. I'm sorry, a conservation of energy question. The center of mass of the rod is above its lowest position. So when it swings downwards and is here, just before it hits the ball, it's going to be swinging, right? It's going to have some velocity. The center of mass of the ruler just fell, right? Now it doesn't fall the whole distance, it falls half, right? Because it's in the middle. So it's not about how high this is, it's about how far the center of mass moved. And then down here, it would have rotational kinetic energy. So up here, gravitational potential. There, rotational. Let's make this easy. Let's make this just a light little ball, mass 0.05 kilograms. And let's make this a meter stick of mass 0.1 kilograms and length 1 meter. Okay? When it swings downwards, I'd like to know how fast it's going. And that's what we're going to do first. This is a conservation of energy question because an object's height changed. And we're asking about velocity. Those are the clues that energy is probably the way to go. Does that make sense? I'm giving you the clues. Now, how far did the center of mass move? Go ahead. Half a meter. Does everybody see why that's true? So I'm going to say that the MGH here, the H is going to be 0.5 meters, because that's how much the center of mass moved. All good so far? Now, this is going to be 1/2 I omega squared. This is how we get to figure out how fast it's going. Now that part's not hard, except I do need to know the moment of inertia of a rod about its end. Do you remember?
1/3 to 12/3.
Good job. That all good? See what we're doing here? Now I'm going to set these things equal to each other to figure out that velocities. This is going to equal mgh. So I think you can see right away the m's cancel out. So I really don't need the mass of that. I'll need it later, but I don't need it now. And this looks like it's going to be 0.5 times g, which is 5, right? Since g is 10. That's going to equal 1/2 times 1/3, so that's 1/6, times 1 squared times omega squared. So can you tell me what omega must be? Please say yes, Mr. Shelton. I think I can. Yay. So do so. I'll pick one of you. We just want to get a number. So I think we're looking at something pretty straightforward. What do you get? What did you get, Aaron?
5.47.
Anybody else get 5.47? All right. Put 5.5 radians per second. All right. All of that was just to figure out how fast the meter stick was going right when it hits the ball. All okay? So we did that problem, even though that's kind of an old question. It's one that from our prior unit, we were talking about conservation of energy. But now there's a collision. Let's say that the meter stick is brought to rest in that collision, but the ball takes off. So the speed of the meter stick after the collision is 0. How fast is the ball going? Okay? Everybody understand what I'm asking? Everybody see this as a collision. The meter stick hitting the ball as a collision. In this problem, the meter stick has angular momentum, but I used a capital L for it because it's got a pivot point, it's rotating about its end. But after the collision, the ball just takes off in a straight line. But I'm going to say it has angular momentum relative to the meter stick. Everybody follow along? So I'm going to start with the angular momentum of the meter stick. That's a 1/3 m L squared times omega, which is 5.47. Angular momentum of the meter stick. Just I omega. Now remember, for the ball, it's R perpendicular times m times v. Okay? What should we use for R perpendicular? Go ahead. It'd be a meter, right? Isn't the ball 1 meter away from the pivot point? Because it's at the bottom, right? The pivot point's here, and the ball's going to take off from here. That's the point of closest approach. That's our R. So I think that'll be 1. Mass of the ball was given. So that's all we have to do to find the velocity. This will tell us how fast the ball is going. Now we had to make an assumption. We said that the meter stick was stopped during this. If the meter stick hadn't been stopped, there'd be whatever the angular momentum of the meter stick was too. But because the meter stick was stopped, all we have is the angular momentum of the ball. That's going to be it for